Today, we're diving in to one of the most powerful features of Cloud Native Buildpacks, building your own from scratch. I'm going to show you exactly how to build, test, and deploy a production-ready Deno Buildpack in just under 15 minutes. Cloud Native Buildpacks transform your application source code into secure, production-ready, very important, container images. So we'll build a Deno Buildpack together, which is a great example because Deno has specific runtime requirements, built-in TypeScript support, and unique permission model that we'll handle properly. So here's what we're going to build today. A build pack that detects Deno applications, automatic Deno runtime installation with version management, proper caching for Deno's module cache, support for JSON configuration, and a complete testing and debugging workflow. This tutorial will teach you patterns that you can apply to any language or framework, so it doesn't matter if Deno is what you're working with. Whether you're supporting internal tools, enforcing security policies, optimizing builds, you'll understand how build packs really work. This is hands-on. You'll see me writing real code, debugging real problems, and at the end, we'll have a build pack that you can use immediately. In order to get started, there are a couple of prerequisites. You will need Podman or Docker, the pack CLI, a terminal that you're comfortable in, and maybe just a tiny bit of bash knowledge would help. So let's start by understanding the build pack lifecycle and how we'll make it work specifically for Deno applications. So the first thing we need to do is make sure we have the pack CLI. Over here, I can run pack CLI. I can see all the subcommands, the documentation, etc. If you don't have this, not a problem. You can go to the documentation, which is available at buildpacks.io. Here you will find instructions for a few different Linux distributions as well as a container image if that's the way you prefer to run it. Instructions for Mac and for Windows. It only takes a minute, go get it installed, and then come right back. All right, now that we have the pack CLI, we do need a Deno application. I've kept this as simple as possible. I have a deno.json, which has my dev task, which just allows me to run my main.ts. My main.ts has the simplest hello world handler that we can put together, which we serve over Deno serve. If we run Deno, run dev, we can then do curl localhost on port 8000 like so. Simple. Now we want to put a build pack together that allows us to build a production grade container image that we can ship anywhere that supports running container images. Really is that simple. Let's have some fun. Okay, so using the pack CLI, we can use the build pack subcommand. Here we can inspect, package, create a new one, pull, register, yank. We'll cover a few of these subcommands as we progress through the video. What we want to do is go to build pack, new. Now to create a new build pack, we have to give it an ID or name, specify the API compatibility that we wish, and provide any targets that this build pack will support. Typically today, in 2025, that is AMD 64 and ARM 64. So let's give it an ID and we'll call this Deno. The path will be in the build pack directory. And we want to target Linux, AMD 64. And we'll cover this in quotes with an additional target of Linux, ARM 64. Now that scaffolds just a few files that we can take a look at now. So here we have the basic configuration for our build pack. We didn't provide or specify an API version, so it's defaulted to 0.8. Next we have with Windows build and with Linux build, and these are just poorly named values. Turning this to true will make it so that this build pack can be built on Windows, which I guess is fair enough. But with Linux build set to true, I believe this means that it can only build on the targets Linux machines rather than all Linux machines, which is what you most likely want. So we can just ignore these and leave them as false and never look back. Our build pack, of course, has a name and a version, and then the targets that we wish to support. The other two things that are generated for us are inside the bin directory, and these are scripts, very simple bash scripts that allow you to actually consume and use this build pack. Because when you're building your application, there may be multiple build packs available. So your build pack has to run some tests or assertions to determine whether the application or context being provided can be supported or built by the build pack. So we want this to fail initially, so I'm going to set this to 1, which is just standard POSIX chat for this script was not successful. Build will leave as exit 0. You can ignore this stuff for now. We'll go into the build step and the build script in more detail when we want to build our Deno application. Now, there's one more thing we need to do before we can use our build pack, and that is configure a builder. Default builder. And we're going to use cmbs sample builder noble. So what is that? So the best way to find out what it is to run it. So let's do docker container run rmit cmbs sample builder noble, and let's get a shell. Now, as you can see, a builder is just a container image that can be run. Builders can be seeded with whatever tooling and build packs you want to make available by default to your internal dev teams, platform teams, customers, etc. Sometimes it really just is that simple. The noble in our tag is just because this is a builder based on Ubuntu 24.04 LTS noble. Easy. Now that we've covered that, we can now use our builder with our build pack to build our Deno application. Well, almost. It's not going to work, but let's see why. Okay, so pack CLI, build, and we need some sort of name, so we'll call this Rockodat. And the path to our application is to go up a directory. Our build pack is in the current directory. Now, because we have our default builder configured, it pulls it, it's using it, and now it's going to attempt to build our application. And we hit our first snag. And it's just telling us here that no build packs were able to detect that they could run our application. So let's fix that first. We open bin detect. Now, we could just say exit 0, rerun our pack build, and it built us an image. Now, of course, there's not really going to be anything interesting in this image, and we'll take a look in just a second. But, of course, we're not very happy with just saying that we can build anything. This doesn't make a lot of sense because it can't build any project. What we actually need to do is check if a file exists, and we'll be looking for a deno.json. In which case, we can say exit 0. Otherwise, we'll exit 1, like so. Well, if we run this again, we are still able to build the image even with our new detection script. Perfect. All right, let's try and do something useful. Here we have our build script. Now, right now, this is just assigning any input variables to variables and saying successful, which isn't really a build pipeline. So what we need to do is make Deno available within our OCI artifact so that it can be executed when we launch the image. All right, so let's paste, and here you'll see that I have the GitHub release for the latest version of Deno 2.36, which is being downloaded with curl, and we'll just output this to deno.zip. And we'll throw that into some sort of temp directory. And then we'll do an unzip into the layers directory, but we need to go a little bit deeper than that. So here we can say, let's make dir deno and unzip to deno itself. So what are we doing here? Well, these input values, especially the layer star, is probably the most important. The layer star, think of it as a Docker file or a container file, where each layer is a snapshot of the output from the previous command, or at least the file system augmented by the previous command. And what we're saying here is that we want to add a new layer. This one is just going to have some sort of name or directory, whatever, as deno, and we want to populate that with files. Now, layers can be used for multiple purposes. So we need to do one more thing to make sure our deno layer is available when we launch our application. To do that, we're going to use a cat here doc, which we're going to write to our layers there, and we give this the same name as the layer directory, only we call this .toml, which means we can add EOF here. Now, inside of this configuration file, we obviously need some valid toml, but what we're saying, types launch equals true. This layer will be available at lunchtime. So let's come back over here, grab our pack CLI, and say that we want to build. And this time we'll get into the correct directory. And we'll remove our test directory because we're good citizens. So pack CLI build with raw codes at path current directory Buildpack is in our Buildpack. Now we've ran into a problem and that curl was not found. To debug this, we can jump back into our builder image and we see that we have access to wget. And I guess we should make sure we have unzip. We don't. So what do? We could make our own builder, but we'll try and avoid that for the time being. We can run the builder subcommand and we can say suggest. We're going to see about half a dozen different builders that we could use, and they each have different capabilities. We can see here, there's a Google builder, which has support for these languages and runtimes. There's the Heroku builder, and then there's a bunch of Paketo builders. What we're going to do is jump inside the Heroku builder. We have curl, we have unzip. This seems like, for our purpose today, a much better choice. So we'll run our config and paste in that we want to use this as our default builder. We can then build raw code app again. Now we can see that we may have to tweak our unzip command a little bit because we've inflated deno. 3 denos is one too many denos because we want our deno layer followed by the deno binary. Now that we know that this is the behavior of unzip, we could either modify unzip to omit the directory or just go straight into our layer star like so. And we can remove the make dir. Now because we've got curl, we can even restore this like so. All right. That's looking pretty good. We inflated our deno. We've made it available at launch time with our launch configuration. Let's see if we have enough to build our image. All right, so let's run docker image ls filtering for raw code app. You'll see that I built this 45 years ago. Well, not quite. This is how we get reproducible builds, by setting the timestamp to a static point in time. Fun. We could then do docker container run rm it raw code app. But it doesn't work. And that's because we actually, while we've made the deno layer available at launch, we haven't told our Buildpack how to launch. So we're going to come in here, and again, we're going to use here doc write to layers dir. And this time we want a launch.toml. And we'll end that off like that. Now we want to start with the processes that we need to run for this application to work. All right, so let's set type equals to web, default equals to true. And then for our command, I'm going to do deno run main.ts. We're just going to assume a main TS for now. And because of Deno's sandboxing and permission system, we'll just say allow all. In fact, for our demo code, we can just allow network binding to port 8000. We can then use the pack CLI to build raw code app, local path with a build pack at Buildpack. Awesome. So let's try docker container run raw code app. Deno not found. Drats. All right, so don't lose hope here. I promise that is the last contrived break we'll have for this video. Now, I just want to go into this in a little bit more detail. We have put the deno binary inside of the layers dir, inside a directory called deno, with then a binary called deno. We then make this layer available at launch. Now this bit is important. This means we can access this at invocation runtime. Meaning, to make this work, we just have to say, use the deno layer. Now, I'm obviously telling you this in this video, but you can make your life a little bit easier when you're building these scripts by throwing around some debugging echo statements to give a little bit of information on what is happening. So here we can say, our layers dir is layers dir. We can then say downloading deno v236. We got unzipping, not quite Copilot, making deno available at launch. And again, not quite Copilot, providing default processes for launch, like so. So now we can go back here for the last time, I promise. We do a build of raw code app, path, Buildpack, like so. Now we can see our layers there. We can see we're downloading deno236, unzipping, inflating, making deno available at launch, and providing the default processes. All right, now container run rm it publish import 8000 on raw code app. Oops. Run. Split our tabs. And there we have it. We now have a production container image to run our demo application wherever we like using Cloud Native Buildpacks. Sweet. Now, before we wrap this up, I promised you a production image, which you've kind of got, but I did say we'd handle the permissions properly. That means we have to understand how to make our build packs configurable. So what I want to show you now is that I have rebuilt our raw code app. And currently, we have no permissions to pass through to the container for deno to run. So I'm going to modify my deno.json. And we're going to add a config, hopefully. Here I'll say version 235. So far we've been using the latest 236. But I'm also going to add permissions. And I'm going to say allow net 8000, the port that we need for our application to work. This config object is arbitrary. I've decided how to deal with it and work with it within our build pack configuration. But we do need to build this to see it working. So we'll do raw code app path dot buildpack like so. Now what we should see in this output is first the version number change. So as we get down to deno, we'll see that we're now downloading 235 as provided in our deno.json. I'm then going to run the same image that we just tried a moment ago that failed. And you can see it's now working. So how did we make this happen? Well, it all starts in detect. The detect script has access to your code base or the context. From here, we can extract the version by using JQ. We say give me config.version, default to 236 from deno.json. We also do the same for permissions, getting config.permissions. I'm taking the JSON array, concatenating them using a space. We default that to just blank. Now we get to write into the build plan. So our build pack provides deno. We're also providing some metadata with the version and the permissions. Now, as you can see, this is not JSON going through into the build pack system. Now, as you can see, the format that we're sending through with the plan is not JSON, which is very annoying, but it's not an absolute blocker. So in our build script, we've got some funky awk. Now, awk is one of my favorite tools because I've written enough of it to be dangerous. And it came in very handy for this demo. We can access the plan via these blessed environment variables, the CMB BP plan path. And I also updated it for the layers directory too. Nobody really likes pulling in inputs to a script. It's all a bit hacky and janky. So these environment variables are a big improvement. We then use awk to make sure that we're on the deno entry, and then we extract the version like so. Print in awk is also just a way to return it to our environment variable, or at least our bash script variable. We did the exact same for permissions. Because we joined with JQ, our array object, to a string separated by a space, we can just pull it out like so. This gives us two variables that we can then use down here to pass in to our deno version, and for our deno run command, inject our permissions. So you'll need to find a way to make this work for you. The detect stage has access to that context. Use it in whatever way you want. It doesn't have to be in a deno.json. You can use any file that you want in any format that you want, as long as you've got the tools to work with it. The plan is then passed through to the build stage where you can use awk or sed, grep, whatever you want to pull those values out and use them as part of your image process. awesome. And that's it. We've just built a fully functional Deno Buildpack from scratch. Let's have a quick recap. We've created a build pack that can detect the Deno applications, install the correct version of Deno automatically, and handles the Deno permission model to produce an optimized and secure container image. But most importantly, you now understand the build pack lifecycle. You can debug things when they go wrong, optimize build performance, extend the build pack with new features. The path from here is up to you. Have a great day.